Hey everybody, what's up? Adrian, hey Joseph, hey Ella, hey Lindy, how's it going, guys? Oh, let's see, it's 3:10. So where is everybody today? It's that class after a test that seems to be a little less attended. I think you guys did pretty well on this test. So I was going to start with. I'm trying to think about if there's any one particular problem that was problematic overall, but I don't think there was. The scores were pretty, in general, pretty good. Did we do this one? I can't remember if there was a problem with 4. You guys want to see any of these? Any questions? Anything that you got stuck on? Okay. Remember, these are going to be a good study guide. Your best study guide for the final. Like I said, a good thing about this final is you've been tested on everything before, right? And you know what kind of questions I'm going to ask, not many like surprises. So this will be a good study guide for final exam time. Let's take a quick look at the schedule. Where are we? Here, we're right on schedule. We're into chapter 4. So we started the anti-differentiation stuff. We're going to shift gears a little bit today and talk about the area problem. And then we'll make a big connection. Probably next class. Yeah, probably next class that connects those two things. That what we're going to do today is going to seem a little disconnected from what we did the last topic we did, which was anti-differentiation differential equations. And then we'll make this big connection is the goal between the two. All right, and then a lot of the end of the semester, we'll be doing a lot of different integration techniques, anti-differentiation techniques. Okay. Yeah, so really, what do we got? Just like 4 regular weeks, and then we got 2 test weeks. That's it. We got 6 weeks left. That's it, including Thanksgiving. Okay, so we're going to do for the next the next 3 weeks are full weeks. We'll do a bit more of a lecture on Tuesday, a lot more group quiz, group work Thursday. Okay. There won't be a quiz today, but let's go ahead and schedule these out so you know. I'll give you a quiz on Thursday. And then I'll give you a quiz on Tuesday. And I'll give you a quiz on Thursday. Okay, the Thursday quiz will be longer. Tuesday quizzes will be kind of shorter. So yeah, it's the next 3 classes. We'll have a quiz. Give you some stuff to do. Okay. Any questions on the test 2? Any problems you want to see? Class in general. Your grades are updated. I think I updated your homework grade. Actually, I can't remember. If I didn't, it doesn't usually change by much, but I'll take a look at that. If anything, it'll change. Your homework grade might have changed a little bit since last time, which won't really affect your overall grade that much. But I'll take a look. I can't remember if I did it this weekend. So your grade should be updated. You should have like a total grade. Okay. So if you ever have any question about any of that kind of stuff, remember, you still got a project coming. I'm going to probably do that over Thanksgiving. And it's not super long. Should be plenty of time. A couple weeks to work on it. Should be plenty of time. Any questions? Okay. Let's take a look. So today we're going to start talking about the second big topic in Calc 1, single variable calculus. And it's called the area problem. And you might remember this from like the first week of class. I talked about like 2 big things, the tangent line problem and the area problem. And we needed limits to get to both of those. Limits got us to the tangent line problem. We took the limit as that space of the secant line went to 0. And limits allow us to get to this, to find the area under a curve, like an irregular shaped area. Give me 1 second because that's what that is. Okay. Yeah. So let's take a look. What is the area problem? So I If you're using the notes or the PowerPoints, this is 4.2, which I don't think I made available yet, which I'm doing right now. Sorry about that. 4.2, 4.3. Sorry. Where is it? There it is. Okay. All right. Give me 1 second. I can't find what I was looking for. All right, here it is. Okay, the second big problem remember, that first big problem, the tangent line problem, brought us to derivatives, and we spent a month on the derivative problem, right? So the tangent line problem let us define the derivative, and we got there using limits. Here's the area problem. The next big part of this course is finding the area under a curve, and then some applications that relate to that, which we'll be doing integration. So when I introduce this topic, I say, okay, how do you find the area under the curve? Well, I want the area under the curve, let's say from 0 to 3 is that x-intercept, right? And we say, well, typically in math, in order to do new stuff, we lean on old stuff, right? So the old stuff would be to find figures that fit under the curve, this irregular shaped curve that I'm looking for, that I know how to find the area. What comes to mind? Rectangles, because they're easy, right? Length times width. You could also do trapezoids. Trapezoids would probably be better, because a trapezoid, think about a trapezoid that only the top of it would be like the triangle, the slanted side, right? And that would kind of, if you did like a trapezoid here and here, it'd probably give you a better estimate. Okay, but the thing is, we don't need trapezoids, right? If we're gonna be able to find the exact area under the curve using the limit process, we can use whatever we want, as long as we can calculate the area of the little geometric figures. Okay, so I like the formula for the area of a rectangle. Ella, what's the area of a rectangle?
Length times width.
Length times width, right? It's really easy. So what I do is, in this case, I got 1, 2. So if you notice, you have 4 rectangles here. Oh, that's not what I wanted to do. You got 4 rectangles. There's like the shaded rectangles, and you can see 3 of them. And then there's like the upper rectangles, the ones that are on the outside of the curve, you can see 4 of them. So let's look at those 4, right? When I look at those, I say, well, I can estimate that area because I know the width of each of those rectangles and the height. The height's given by the function, 9 minus x squared. The width is given by how I divided those evenly, right? So from 0 to 3, I divided into 4. So each one of those would be 4 over 3 in width, right? 1 1/3. And then the height of each of these, like right here, what's the height? That's 9, right? That is, if I plugged in 0 to my function, the output would be 9, right? Here's my function, 9 minus x squared, right? So the outputs of functions, remember, is the height of your function. So the output of the function, if I break it into these different little intervals, the output of the function will be the height of my rectangle. Okay, and that's where we're going to start today. We're going to start with estimating. And then what we're going to do is just get more rectangles, right? We're going to say, well, if I got a whole bunch of those rectangles, then my estimate's pretty good, right? Back here, my estimate, it's not so good, right? If I use those upper rectangles, it's significantly over the actual area. But if I let the rectangles just be to 15, I got a really good estimate. All right, and here's the big jump we'll take from estimating area by adding up a bunch of areas of rectangles to the exact area. We're going to take the limit as the number of these rectangles goes to infinity, right? And that's pretty conceptual. Like that's an infinite number of rectangles. But what happens is you get the exact area under the curve, right? You can almost see it because as it goes, as n increases, it pretty quickly, the width goes to 0 as the number goes to infinity. And that'll give us the exact area, which is, I think, is really cool, right? You don't know how to find area of these weird shapes. The only thing you've ever found area of are geometric figures that we've been able to find a formula for, like circles and squares and rectangles and triangles, right? And that's it. Now we're gonna be able to find the area of pretty much anything under, if we can find a function for it, we'll be able to find the area under the curve. Okay. All right. So let's start with the basics. So we're going to be adding, right? We're going to be doing a lot of adding because I have to add the area of all these rectangles together, right? And if I got to add the area of the rectangles together, you got to learn some notation for doing that. And you may or may not have seen this before, the sigma notation, which indicates a sum. So that's what we're going to start with. And then we'll come back to the rectangles. Okay. Sigma notation. All right, here's sigma note. So let's take a look. You're going to see this a lot. By the way, when you get to Calc 2, you do what's called sequences and series. And series is what we can call this thing right here. This is a series, right? It's the sum of a bunch of terms, all right? So you're going to be using this. It's kind of in a different way, but you're going to be using this notation a lot. So it's good to get used to it. Good to have some exposure to it. Okay, what does this mean? I got from I equals 1 to n, a sub I. All right, so you can kind of think of it as a function that adds a bunch of stuff together where your inputs are always integers. Okay, and most of the time, the inputs are your whole numbers or your natural numbers, either starting at 0 or starting at 1. 0, 1, 2, 3, 4, or starting at 1, 1, 2, 3, 4. Okay, we can start them anywhere we want, but typically you'll see a 1 here or a 0 here. I is called the index of summation. A sub I is the ith term. And the upper and lower bounds. So this is the lower bound, start at 1, the upper bound's in. Okay. So this is the generic form. We don't know what this sum is because we don't know what the ith term is. All right. But here's an example where you do know. So I could ask you to find this sum right here. Say, what's that equal to? Well, as I goes from 1 to 6, and the ith term is just I, right? Then you're just adding. You start with 1, and then it goes to 2, and then it goes to 3, just integers. Right? So 1 plus 2 plus 3 plus 4 plus 5 plus 6. So literally this thing is equal to this. That's what that means. And of course, we could add it together. What's that? 11, 15, 18, 21. Okay. So far, so good. I guess the tricky part is going backwards. I'm going to give you this. And you're going to give me that. I'll use J for the index of summation as well. Doesn't always start at 0 or 1, as you can see. Oh, here's an interesting example, I guess. You can have the same sum. What if I said, give me the same sum, but start at 0? It's literally like a shift. You can shift 1 to the right. If you're shifting this guy to the left, then you shift this guy to the right, and it should be the same. Right? So if I start at 0, how do I get 1 to be my first term? Well, I'd have to add 1 to it. All right, so if you plug in 0, then you plug in 1 and you get 2, then you plug in 2 and you get 3, and it's the same thing, right? In other words, this is equivalent to that. The little substitution there. Okay. I mean, this one we can figure out without too much trouble. This, not so much, right? 1 over root j as j goes from 1 to 5. 1 over root 1, 1 over root 2 plus 1 over root 3. That's going to be a complicated common denominator or just a decimal value. Okay, but the point is just understanding what sigma notation means. It means add. Start here, end here, plug stuff in here, just like you kind of would with a function. Okay, F. This one we're going to see in the future. We're going to write a function representation as a sum. Okay, or, well, I take that back. This is a function, right? But this x sub I means I'm going to plug in x sub 1, and then I'm going to plug in x sub 2, and then plug in x sub 3, just like we have here, right? And these are actual x values. So this is a notation how to go through the different x values, which we're going to see this again when we do these sums, because remember, these are going to represent the height of my rectangle, right? When I plug in an x value to function, it gives me my function value, which is the height of my function, which will also be the height of my rectangle, because the rectangles go up to wherever the function is, right? And this is the width of a rectangle. We can use delta x. Delta x is our change in x, whatever we decide that to be. All right. Oh, some properties. These are pretty basic. We've seen these with integrals and different derivatives, and they're going to follow with us. If I got and we know this from just doing factoring, right? If I got a constant multiple over a sum, I can factor out that constant. No big deal here. Right? We can take out whatever, if it isn't the part of the summation, right? Then we can factor out that constant. This one should make sense, right? How do I read this? The sum, I guess the sum of this sum is equal to the sum of the two sums, right? In other words, I can add all these guys up and add all these guys up, or I can add them together first and then add them all up, right? As I go from I to N. Oh, here's a good question I got for you. We got some formulas coming up. What if I wanted you guys to add 1 to 100? Could you figure this out? This is a classic math problem. I think it was the French mathematician Gauss in the early 20th century. His math teacher said, "What's 1 plus 2 plus 3 plus 4 all the way to 100?" And he had the answer in a minute. What do you think? This is tough. This would be hard to figure out. There's a real tricky way to do this one. So if I wanted to add up 1 to 100, and that would take forever to actually just do it without a calculator, right? 1 plus 2 is 3, plus 3 is 6, and so on. But here's a really clever way to do this. I'm going to do it twice. So I'm going to do 2. So what I'm going to have when I add this together, right? So the question is add up all the integers from 1 to 100. But Gauss said, well, why don't I do it twice? But I'll just flip the order, because then you notice you get the same number every time, right? So 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 is 101. You get a whole bunch of 101s. 100 plus 1 is 101. Okay, and we know multiplication is the shortcut for addition. How many 101s do we have? There's 100. Does that make sense? So this sum is, if you use multiplication, this little trick, you got 101, you got 100 of those, right? So I can multiply, but I did it twice, right? I got two sums, but I only want one of those sums, so I got to divide by 2, and that's it. So if you want to impress your friends and you want to add up 1 to 100, all you got to do is multiply 100 times 101 divided by 2. That's 50 times 101. That's 5,050. Okay, but that doesn't just work for 1 to 100. It works for 1 to any number, right? That is, if you just add consecutive integers, what you can do is you find the nth integer, multiply it by the n plus first integer, and divide by 2. And that's our first formula. We're gonna use that guy as we do these, and I'll show you when. It's not gonna be clear until we do one, like when we actually use those. Here is the rule for that. for any value of n. So we just did 6, right? Remember we did 1 through 6, we got 21. Use your formula. 6 times 7, 42, divide by 2, 21. It will work every time. These ones are a lot harder to, by the way, that was in no means a proof, right? We didn't prove it. I just showed you kind of an example of how it worked. We could probably do the proof for that. We don't do a lot of these discrete proofs in here. So just take my word for it. That's true. And then this one would be a little harder to figure out, but we'll use it. And then this one as well. In other words, I can add up all the integers by using this formula. I can add up all the integers squared by using the formula, positive integers. I can add up all the positive integers cubed with this formula. And what's this one mean? Well, that just means, so what do you think? Jake, any ideas? If I asked you to add the number 5 6 times, what would you get? There's no index over here. I see you're talking. I see you're unmuted, but I'm not getting anything.
Would you just be able to add 5 6 times?
That's
so
right.
It'd be 5 times 6.
5 times 6. Very good. You got it. You got the formula. That's what that means, right? So you're just adding, just like Jake said, you're adding that number this many times, right? This many times. And there's no, you're not plugging in I anywhere here because there's no I to plug in. So it's just 5 plus 5 plus 5 plus 5 plus 5 this many times, or shortcut for addition is multiplication. Okay. This is something I'd give you on a test, right? I don't give you a lot of formulas in here. These ones I would. I don't expect you to remember these. You're going to see them a lot when we get into these problems, though. Okay. Oh, why do I have the answer here? Let's just remove this altogether and work this one out. Evaluate this for 10, 100, 1,000, and 10,000. Okay. Now, here's where we're going with this. We're going to evaluate this as n goes to infinity. That's our goal. N's going to represent for us the number of rectangles. So ultimately, we're going to take the limit of this thing as n goes to infinity. Okay, and the only way to do that is to understand, is to be able to use these formulas, right? Because we're going to have to get rid of this sigma notation and be able to work with these algebraic representations. Okay, so this is kind of a warm up to that. 10, 100, 1,000, 10,000 is going to infinity. All right, so let's see how we do. There's a lot of algebra. All right, so this is, I got to find, here's my goal, is to find these. This is my goal. I gotta tease this out using algebra, or maybe this guy or this guy. I gotta isolate the i's. Gotta isolate the i's, or maybe the constants. Gotta isolate those. Okay. So here's my first. I don't like this. The sum. Remember, I got the sum of a sum, which I'm allowed to do this. This is gonna be my first step. I'm allowed to write that as 2 separate sums using sigma. And it's basically, do you agree that those are the same? Well, with a plus in the middle. I'm not plugging in the numbers yet. We could do that. We could just plug in 10, but that would take forever, right? If n is 10, then we go 1 plus 1 over 100. And we go 2 plus 1 over 100, 3 plus 1 over 100, add those together. Okay, which wouldn't be bad, but once you get to 100 and 1,000, you might recognize a pattern, but we already kind of got the pattern. We got the formulas that come from the pattern. All right, so I do that first. And here's something that we're going to do all the time. So stay with me. It's the constant multiple rule. N's fixed, right? N is fixed. I know it looks like a variable, but there is some value for n that we're interested in. Okay, I is your variable here, right? I is the thing you're plugging values in for. So that means I'm allowed to factor it out. Okay, I'm back. Sorry about that. I am allowed to factor out n's because my index is I. All right, my indexing of that is the variable. Anything else you can factor out. So that leaves me with an I. And that I'm going to factor out of here too. I guess we could have factored that out in the beginning. I decided to do it in 2 steps. All right. What do you think? Lindy, what happens? What is, as I goes from 1 to n, I, what is that equal to? Without the sigma notation from our formulas.
As I goes to 1 to n.
Yep, and you're just adding I, so that's 1 plus 2 plus 3 plus 4 plus 5 all the way to n. What's that equal to? You see it on here?
Would it be the second one?
Yeah, it's this guy. Does that make sense? We found it.
Yeah.
Right. So whenever you see that, you want to replace it with what it's equal to without, right, the multiplication equivalent of the sum. Good. Joseph, what would this be equal to, do you think? So it's 1 plus 1 plus 1 plus 1 plus 1 n times.
I'm not sure.
Here's your hint. It's on here somewhere. It's just a constant. You just add to itself n times.
So it'd be the first one?
Mm-hmm.
Oh, okay.
And the constant is 1. So you just get in. Does that make sense? You just get in. However many times you're adding 1 to itself. Like if this were a 6, then this would be 6, right? 1 plus 1 plus 1 plus 1 6 times. If this were 100, then this would be 100, right? 1 plus 1 plus 1 100 times. If this is an n, then this is an n. Okay. And that's it. We're able to evaluate this sum using our formulas here. Well, I'm going to reduce it. Let's see. I guess I could run this through. I don't know. We got to plug in numbers. It's how do you want to plug them in? This one I'll reduce. And if we want, I guess we could add those together. That wouldn't be too bad to add them together. But ultimately, I'm going to take the limit. And we really could jump into this right now. What if I ask the limit as n goes to infinity? Well, then we just carry this limit with us. Limit, right? Because we're just doing algebra. We haven't taken the limit. And then at this point, we take the limit as n goes to infinity, right? Which you guys know how to do. The limit as n goes to infinity. This is n squared plus n. What do you think, Adrian? What's the limit of this first term as n goes to infinity? N squared plus n over 2n squared. Rational function, degrees are the same.
I am not sure.
Anybody remember that? What do you think, Lindy? You remember that one?
It would just be 1/2, right?
1/2, right? So Adrian, remember
Oh yeah, it was from the last term.
from the last test. That's right. If the powers are, if the degree of the top's the same as the degree of the bottom, then you go with leading coefficient.
Oh, so it's 1/2.
That's 1/2. That's right. And then this was a different case. Your degree in the denominator is greater than degree of the numerator. So that guy goes to 0. So I kind of just changed the question on you. So I apologize for that. We did better than plugging in 10, 100. If you plug in 10,000, you're going to get something like really close to 1/2 is my guess. But we did better than that. We did bigger than 10,000. We took the limit as n goes to infinity and we got 1/2. Okay, so that's some pretty heavy duty math if you think about it. We're doing not only this sum as I goes from 1 to n, but then we're taking the limit as n goes to infinity. And what do we get? Half. It's got a half. That's an infinite sum, adds up to 1/2. Okay. All right. Oh, here's your answers. Let's see how we did. If you do plug in 10,000, oops, you get 0.50015, which makes me feel pretty good about our 1/2 answer. Okay. That's the warm up. Now the real problem. Here's the real problem. All right. So find the area under the curve. This is the function f of x equals negative x squared plus 5. Okay. And eventually, here in a little bit, we're going to be able to get the exact area under this curve. The exact area, which is pretty cool, right? As I go from 0 to 2. But first, we got to warm up and just get some estimates. All right. Because we want to understand, we want to be able to see that what we're adding up areas, right? And the area of, oh, what do you think, Ashley? Can you tell me what the area of this rectangle is? Right here, this first one.
Two?
Did you say 2?
Yes.
Oh, that's not bad. I would say it's, how'd you get that, Ashley? You did what times what?
5 times 2/5.
Good. 5 times 2/5, that's an estimate. You're close. It's a little under 5, but you're really close. That's a really good estimate. I can do a little bit better than that. I'm not sure what the height is by the graph. So actually, that's really good that you say, oh, it's about 5. 5 times 2/5 is the area. But if I want the exact height, I could say f of 2/5 times, and I can see here what the width is, and Astrid saw that as 2/5 times 2/5. Right? That's the actual height of that rectangle. Because remember, input 2/5, output function. Function represents the height of the curve. And in this case, the height of that rectangle. So f of 2/5 is negative 2/5 squared plus 5, which we think should be pretty close to 5 times 2/5. I'm going to use my calculator because I don't want to deal with 4 25ths plus 5. So let's see. 2 divided by 5 squared, and then 5 minus 0.16. And actually, you were pretty close. I got 4.84 is this output right here. This is the point 2/5, comma 4.84. And if I multiply that by 2/5, I get something pretty close to 2, which is 1.936. But that's just one. Okay. So I'm going to ask you to do some estimates, which is kind of a pain. But I just want you to get the idea. I'm going to say estimate the area under this curve. And a lot of times in the textbook, they'll say, well, get the estimate by the lower sum. It's called the lower sum since all these rectangles are underneath. And then they'll say, get the area by the upper sum. And all these rectangles are above, right? And how would we do that? Well, how would we structure it? Well, it's pretty straightforward. We're going to have a formula for this eventually, but it's pretty straightforward. And that I would say the height of this one, the first one, is 2/5. And I can just tell from my picture, because I look at the first rectangles, the height's there. If it were the upper sum, the height would be here, right? Here's the upper rectangle. So the lower sum, I start at the right endpoints. Does that make sense? Just because my function is decreasing. If my function was increasing, it'd all be different. But I'm going to tell you eventually it doesn't matter where we start, right? Because when you take the limit, as we go to infinity, they're all the same. If it's above or below, it doesn't matter. So with estimates, I don't really care how you do it. I'll say, give me an estimate for this area using 5 rectangles. So you can decide if you want to do upper or lower. I'm going to do lower, right? Because I'm just going to start with the right endpoints. And here's the area of my first rectangle. What do you think, Gabby? Can you give me an expression for the area of this rectangle? I need it, the width of the rectangle and the height of the rectangle using like the function.
I'm just a little confused between like 2/5 and 5/4, you know?
You mean 4/5?
Yeah, we could put 4/5 times. Oh, yeah, times.
So let me ask you this: what's the width, Gabby? What's the distance from here to here? How
It-
wide is that?
I'm not quite sure, but we could maybe subtract 2.2/5 with 4/5.
That's right. 4/5 minus 2/5. The width is 2/5. That's correct, right? Just subtract those distances, or you could recognize that it's the same width as this one. I mean, you can't always trust the pictures we're looking at, but if you notice, they're all the same width: 2/5, 4/5, 6/5, 8/5, 10/5. They're all going up by 2/5. But good, that's how you get it. You could subtract. Now, Gabby, I need the height of this rectangle, which is, does it make sense that that's going to be the output right here on your curve, since it touches your curve right here?
Yeah.
So does it make sense? It's f of not 2/5 this time, but f of 4/5.
Okay.
Everybody see that? Jonah, what do you think? What's the area of the third rectangle? Using the same kind of process. What's the area of that guy?
So it's going to be f of 6/5 times 2/5.
Very good. Plus f of 8/5 times 2/5. 1, 2, 3, 4, and then 5. F of 10/5, which is just 2, times 2/5. Okay. We did the math for this one. On my last slide, I got 1.936. Oh, let's see. I don't really want to do this one's easy. I'm going to do that one for me. What's f of 2? F of 2 should be 1. Does that make sense? If I plug in, right, here's my function, right? So the height, this output, is the height of my rectangle. Plug in 2. Remember, it's 2 squared, then make it negative, right? Negative x squared. 2 squared, then make it negative. So that's 4. Make it negative. Negative 4 plus 5 is 1. 1 times 2/5 is 2/5. That one's 0.4. And then I'm going to skip these. I'm going to trust that you guys can do those without me doing it, because I don't want to do it. That's a hassle, right? It's just plug in the 4/5 into your function, 4/5 squared, make it negative plus 5, that's the height, times 2/5, and get an output. I'm just going to tell you what the answer is. 0.4 plus 1.936 plus this one plus this one plus this one, whatever they are, is 6.48. Okay, that's the estimate. Now, the reason I want you to do that is because here's where we're going. We're gonna have n partitions, not 5 partitions. So try and picture this. Instead of 5 rectangles, we want n rectangles. Okay. And then instead of particular values of x's, We're going to have to think of some way to represent the inputs algebraically as we move through this interval, the entire interval. How did we do it this time? Well, we just added 2/5. But what we're doing here, see if you like this. I can represent these things in my index or my summation notation, right? First of all, I needed a way to use I to represent 2/5, 4/5, 6/5, 8/5, and 10/5. As I goes 1, 2, 3, 4, 5, right? The sums are taken care of, right? All these pluses, well, that one's easy. I just use that capital Greek letter sigma, and that's going to represent a sum. Okay, so let's try and generalize this problem. This sum would be equal to big sigma these are all F's, and it looks like I'm taking my number 2/5 and just multiplying it, right? 2/5 times 1 is 2/5. 2/5 times 2 is 4/5. 2/5 times 3 is 6/5 times 4 times 5. Right? And I need 5 parts of this sum. Okay. And then, well, what did we do here? We decided we wanted 5 rectangles. So we took the total width of my total area, which I could say, this is kind of like Gabby's idea, just subtract. Start with the bigger number, subtract the smaller number, and divide by how many rectangles you want, right? That's how we could have got the 2/5 if I didn't give it to you. If I said, break that thing up into 5 equal parts. Well, it's the length's 2 divided by 5. And of course, 2 minus 0 over 5 reduces to 2/5. And look what we just done. I built a representation for this shaded region, not the whole shaded region, just all my rectangles, which we figured out like this by just using length times width, using the function output as our length, and then we're able to write it like this. Okay. Now, let's try and do this part. Instead of 5 rectangles, we want n rectangles. Well, that's not too bad. Right? Instead of 5 rectangles, n. So it's this, the width is still 2. I'm still going from 0 to 2, but I'm dividing it up into n rectangles. So the width of each rectangle is, instead of 2 over 5, just 2 over n. Okay, and for this problem, now we're going to have a little variety in here. The algebraic representation that allows me to go through and input different x values as I go through this entire interval that has n rectangles would work similarly to this one. If there were 5 rectangles, the width's 2/5, and that gets me to the right endpoint, right? 2/5 times 1 is 2/5. 2/5 times 2 is 4/5. So each time I put an I in, I get to the right of my endpoints. So if the width is represented by 2 over n, then the right endpoint, we could do left endpoint, it's a little more complicated, and we'll look at that. The right endpoint of each of these would be represented by 2 over n times I. Right? It gets me to the right of these if these are all n's, and there's a whole bunch more of them. Okay. And again, that's still an estimate. If I'm using the word exact here, if I take the limit as n goes to infinity, I can use the equal sign instead of my squiggly equal sign. I get the exact area for this problem, and we'll generalize this for every problem. And then we'll have to do one. It's a lot of work. These are a lot of work, actually find the exact. Okay, who's got questions so far? So far, the only question I'll ask you on your quiz on Thursday will be to estimate. Jake, you're good. Will be to estimate this based on 5 rectangles, okay? The real question is going to come here in a minute. Okay, let's see where I am in my lesson. So we found the lower region. If we did that same thing again, the estimate for the upper region, okay, that's this picture. Then it looks like I got 8.08, or the book got 8.08. How did they get that? Well, these are left endpoints now. So the first one is f of 0, right? It just gets shifted over, but it's still times 2/5. And then it's f of 2/5 times 2/5. And then it's f of 4/5 times 2/5. And then we're here, and it's f of 6/5 times 2/5. And then it's f of 8/5 times 2/5. Okay, and of course you don't get to the last one because you started here. So 1, 2, 3, 4, 5, and your overestimate, right? That's your last rectangle. And that should be, and we know how to do that, right? That's going to be 5 times 2/5 is this one. 5 times 2/5. This one is 2, area 2. And then add them all up. Okay. All right, here's the concept again. We're gonna do the exact area for this one by the limit definition. Here's the concept. We want this, right? This is just telling us it doesn't matter if I do the lower sum, which could possibly be by the right endpoints or the left endpoints, or the upper sum, because as I take the limit of either one of these, they both go here, right? As I take the limit as n goes to infinity, it doesn't matter. They'll all go directly under the curve. Okay, so I can choose whichever one I want, and there is one that's easier. All right, so let's do it. We know it's somewhere between 6.5 and 8. Somewhere between 6.5 and 8. Let's see what we get. Okay, get ready. These are can be kind of lengthy. I know by definition that the area is the limit as n goes to infinity of, and if we didn't just do it, we'd have to decide what the lengths were. We know that the total interval is 2. So delta x, which I'll use to represent the width of each interval, is the length of the interval broken up into n equal parts. Okay, 2 over n. The height of in your textbook, you use this. It goes f of x sub I, where x sub I is represented, if you're doing right intervals, then it's simply the width of each interval times I. This works if you're dealing with right endpoints, and also if you're starting at x equals 0. Okay, if I start at x equals -5, I'm going to have to figure out how to adjust it, because when x equals, or when n equals 1, I got to be at that first interval. So we're going to have to maybe do some shifting. If I want to do left endpoints, which I'm not going to do, I mean, it would not be a bad idea to do them just for practice. But if you think about it, well, let me talk about that after we do the problem. Okay, because this wouldn't be, I can't get to the left endpoint with that, right? Unless I started at I equals 0, then I could. But typically we're going to start these at I equals 1. So I'd have to shift it, which isn't terrible, right? I'd have to do like the I plus 1 or the I minus 1 to shift it back 1, right? 1 width. Let's do that later. Let's just worry about this problem. I'm choosing to do right endpoints, and we're starting at 0. Okay. So I think it's helpful to see the 5s. If n is 5, then it's pretty clear that it's like 2/5, 4/5, 6/5, 8/5. I is just going up by 1, and then you're just going right through the interval and getting different heights. So just let 5 be n, and it works the exact same way. So the exact area is the limit as n goes to infinity of the sum of each height times the width of each, which in this case is uniform. Okay, so now our goal is to find that limit. The limit's going to be the very last step. So our goal will be to mess with this thing. Okay, my goal is to somehow evaluate that sum using those formulas I gave you. Okay, so first step always is to replace this with what it's equal to. What do you think, Eiley? Could you tell me what f of 2 over n times I is?
Wouldn't that be the function of 2 over 5 times I?
2 over 5 times I? Not 5 anymore. We got an n in here.
Oh, okay.
So you got to plug it into my function. What do you get?
Two, like opposite of 2n I squared plus 5?
Very good. That thing. Negative 2 over n I squared, right? Function evaluation. I'm not plugging in 2/5 and 4/5 into my function. I'm plugging 2 over n times I into my function, right? And that's where this gets a little complex, Negative, sorry, I just kind of did it in the corner, moved it down to the corner, and then I'll come back and put it into my sigma. So it's negative x squared plus 5. X is 2 over n times I. So now I have to, and remember, we're not squaring the negative. We're squaring the input, then making it negative. That's important. So that's 4 over n squared times I squared. Remember, when you square a fraction, you got to square the numerator and denominator. When you square a product, you square each part of the product. This is my function evaluated at 2 over n times I. That'll get me the heights every time I go through my interval, right? As I goes from 1, 2 to 3 to 4, which we're not going to have to do, by the way, because we're going to use the formulas, right? I'm not going to actually have to plug in 1 and 2 and 3, right? That's what these things are for, right? These allow me to not do that, right? I don't have to evaluate at 1 and 2 and 3. I can use these products shortcuts, right? Use the formulas, and that's the goal here. That's why these formulas are really important, right? We're going to try and tease out our i's, I squareds, I cubes, and our constants. So we got to do a lot of algebra here. Okay. So this is negative 4 over n squared times I squared times 2 over n. Oh, wait, I missed something. Plus 5. Try that again. Let's just highlight in yellow and tell me if you think they're the same. My yellow highlights are the same thing, right? F of 2 over n times I, in this case, is equal to negative 4 over n squared times I squared, plus 5. Okay, any questions so far? We got to find our, remember, I'm looking for i's by themselves with sigma, I squareds by themselves, I cubes by themselves, and constants by themselves. The n's, I'm not interested in, right? In fact, that's what I'm gonna do first. I'm gonna factor him out. Factor him out right away. You gotta be real careful with your algebra. All right, I got a couple different n's that I want to factor out, but only this one's multiplied by both. So I can factor him out. and just be real nice and neat and organized because these problems require that. I want to get rid of the 1 over n squared, or the -4 over n squared. That's a constant, right? I'm allowed to factor out n's, but I can't, this isn't multiplied. This thing isn't multiplied by the entire sum. So I can't factor it out. This was multiplied by the entire sum. In fact, let me go back to that for a second, because you're going to do this with every problem. That width, the width of your rectangles, you're always going to factor that out, always. So you could do it right away, right? You're always going to factor out the width. Then if n's show up in the rest of your problem, like it does here, you're going to have to break up the sum. So we know that the sum of this sum is equal to the sum of two different sums. In other words, yeah, let's just do, I'm doing maybe a couple too many steps, but that's okay. You can hear me. I will be right back. Okay, I'm back. And then the 2 over n was multiplied by this whole thing, right? So I better do that to be safe, because it's still the 2 over n times all of that. Who's with me? Who's not with me? Who's got questions? This is a long problem. These are hard. These are hard. We just really shifted gears here. This is just a algebra mess, right? There's no calculus in this problem until we take the limit, right? This is just all algebra. Algebra, almost the whole way. Okay, now I'm allowed to factor this guy out of, now that I broke up these sums, I can factor this guy out. That's good, because then I'll have an I squared. And then I'll have a constant. And now I can use my formulas. Let's see what we got. That's the goal for every one of these problems. The goal will be to get to this point, because now I have the sum of I squared, which we haven't seen this one yet today, so I'm going to really rely on my formula sheet. I'm going to replace that with what it's equal to, get rid of that sigma. I know what the 5 is, right? That's just 5n. This guy's just going to be 5n. And go to my formula sheet and see what I squared is. You'll probably have this one memorized by next class, because you're gonna see it so much. N times n plus 1 times 2n plus 1 over 6. N times n plus 1 times 2n plus 1 over 6. That's what just this is equal to. N times n plus 1 times 2n plus 1 over 6 plus 5 over n. And we finally made it. Now we're back in chapter 3. This is a limit you know how to take. All right. Usually you had x's in there, but this is a limit of 2 rational functions. Limit of 2 rational functions. It's just messy. All right. So ask yourself, can you take that limit? What's the algebra involved? You're going to have to run that 2 over n back through. Oh, I got a mistake here. What's my error? I knew something looked funny there. Anyone see my mistake? Where is it? This guy, right? The 5, this sum It's 5 times n, right? So you're gonna say, yeah, 5 times n, right? Not 5 over n. 5 times n. All right, go ahead and give it a try. Give me the exact area. Find that limit. Your answer should be between 5.5 and 8. See if you can get it. Okay, see how your algebra is doing. A lot of room for error here. I multiplied these two fractions together, so -4n went up top. I didn't distribute yet. And then n squared went on bottom. So I got when I multiplied these two, I got this. And then I ran my 2 over n through. So that 2 times -4 became -8. and then an n times 6n squared became 6n cubed. And then the 2 over n times 5n, the n's cancel out, that just gives me 10. Okay. And I can save you some trouble here. If you're multiplying these out, you can, that's fine. You could FOIL n times n plus 1, and then you could multiply it by n. Or you can recognize, and by the way, all the areas I'm going to give you are bounded regions, which means they can't be infinite, which means the limit should always exist. The limit should always exist. So if I had like an n to the 4th up here, I probably did something wrong, because the limit as n goes to infinity, if the degree in the numerator is higher, it doesn't exist, right? But it has to. The limit has to exist because you're going to be looking at the area. It's a finite region, okay? So I can recognize, I'm trying to evaluate this limit with doing as little work as possible. The answer is going to be negative 16 over 6, or negative 8/3. How do I know that? Well, I look at the numerator, I decide the degree's 3, right? The degree is going to be 3 in the numerator. You got an n times an n times an n, degree 3. And then I concentrate on so then I know it's going to be the leading coefficient because I have the same degree in the numerator as the denominator. They're both degree 3. So I just focus on what my coefficients are going to be. The numerator ultimately, in the end, if I were to FOIL that out, I'm going to end up doing 2 times negative 8, negative 16. And in the bottom, I just got that 6 hanging out, right? So you can multiply if you want, to be sure, but I'm telling you, you're going to get a negative 16, right? Does that make sense? Because in the end, if you foiled these two guys, then ran the 8n through, the highest power is going to be a negative 16 n to the 3rd. Okay, so that tells me that this limit of this first fraction is negative 16 over 6, which of course will reduce to 8/3. And then be careful with this guy. This is a limit now, not a sum. What's the limit of 10 as n goes to infinity? Which is 10, right? It's constant. And that will give me my final answer, which should be, I think I got 7 1/3 if you do that exact. Oh yeah, so I got a question. Can you just make it one limit and then, or one fraction and then do the limit? Absolutely. Yeah, if you prefer to do it that way, let's see. That would be, so back up to this step. The question was, can we just add these together? Absolutely, right? This, you'd have to put a down here n squared and then make that an n cubed. Absolutely. Yeah, I think this way is a little bit easier. I think algebraically, if you leave them separate, it's a little bit easier, but whatever is your preference, that's fine. As long as you're following your algebra rules, yeah, absolutely. You can add those fractions together. I like to split them up because I saw that with that times that would just give me 10, and that's easy to deal with. But good question. That would be what? Negative 8/3 plus 30/3 or negative 20. Usually not negative, positive. 22/3. That's how I usually give my answer, right? In math, we like improper fractions better than mixed numbers, but at least I get a sense of the area with the mixed number, right? Which, by the way, just step back from the math and think about this for a second. That's pretty cool, right? You've never found area. That's a weird looking, I mean, look at this area. If I graph this area, look at the shape of that thing, right? It has 2 straight walls and then it has a curve on the top. And it just follows the quadratic function kind of curve, right? With coefficient 1. There's no formula for that, right? We can't figure out a formula for that, but we can find any area exactly by using this process of infinite rectangles, which is pretty powerful, right? It's a real interesting discovery. right? And that's the same idea as the tangent line function, I think, tangent line problem. Although this one I think is more creative, right? If you're trying to come up with this, like you can kind of picture that secant line to tangent line, but the idea, the concept of an infinite number of rectangles is pretty cool, right? Which gives you the exact area. Okay, but here's the problem in a calculus 1 class. Oh, look at all this work we have to do. All right, so there's a lot of room for error in here. So you just gotta be super careful with your algebra. Okay. Let's just set this one up for the left endpoint, and then we'll decide if we want to do the whole thing or not. Probably not. And then I'll give you a break. All right, start over, left endpoint. We should get the same thing, by the way. Left endpoint. Just want to show you there's a couple ways to do these, and then it doesn't matter how. So I start completely over. Right, the width is still and we're still starting at 0, which makes these a little bit easier as well. Okay. So now, if I'm starting here, then when I is 1, x has to be 0, right? That is, I need this representation for this thing such that when I is 1, the input 0. When I is 2, the input would be 2 over n. Right? When I is 3, the input is 4 over n. Does that make sense? Right? I mean, the inputs, they just start one later than they used to. I didn't do this before. Before it was when I is 1, 2 over n. When I is 2, 4 over n, right? That started at the right endpoint. But now we're shifting, and we want I to start at 1. So what do you think? How do you do that? It's still going to be, I think it's still going to be some kind of 2 over n times something. It used to be I, we had to shift it. We had to shift it 1 unit. So it's helpful to look at this first one. When I is 1, this has to be 0. When I is 1, so usually it's going to be like plus or minus 1 here. Okay, so I'm going to do a little trial and error and do that. Is that the proper shift for me? That is, when I is 1, right, this is going to be, that's my guess. I'm thinking that's my algebraic representation for my indices as I go through. So when I is 1, check. When I is 2, 2 minus 1 is 1, and I get 2 over it. When I is 3, 3 minus 1 is 2. 2 times 2 over n is 4 over it. So I think I succeeded. I think I successfully succeeded in shifting this guy over 1 unit to the left, so I could start at the left endpoint. So this does something different. This does this guy. We're doing this one. Right? We didn't even do the estimate. I told you what the estimate was, but now we're doing this one. Where before I take the limit as n goes to infinity, any estimate would be over the actual area, as opposed to the last one where it was under the actual area. But my point is, if you take the limit as n goes to infinity, you'll get the same thing. You should get the same thing. My other point is, I don't like doing it this way. Right? And I'll show you why. If we work this out, what's the area representation? Well, it works the same way. You got A, the height of each rectangle is what we figured out for our, oops, I forgot my sum and my limit. The limit as n goes to infinity, sum of all my heights for each rectangle represented by the function notation times the width of each rectangle, still 2 over n, as I goes from 1 to n. Okay, and it's pretty clear why I don't like this way. If it gives us the same answer, why am I going to do it? Right? Can you see why we don't like this way? What is this equal to? This would be, remember my function is negative x squared plus 5? I don't want to deal with this. It's not terrible, right? That would be 4 over n squared, and then square I minus 1, I squared minus 2i plus 1. You get an extra term out of it, right? You get an extra term, so you can have 3 sums. So for the sake of time, I don't think I'm going to finish this. If I ask you to do a problem, it's your choice, right? It's your choice, and there's no reason to choose this option, unless you just want to see if you can do it. You try this for homework if you want. See if you get the same thing. It should be the same thing. This should equal. It has to. It has to equal that, right? And of course, what's messy about it, the next step, is what makes it. I guess it's not. I mean, terribly more difficult. If I square this and then add 5, this would be 4 over n squared. This would be I squared minus 2i plus 1. And then it's going to be plus 5. And then it's going to be times 2 over n. That's a negative. That's, if I did that right, that is f of 2 over n times I minus 1. Lindy?
Will the homework make us do this way?
No. The homework will just actually, the homework in WebAssign will just tell you to find the area, I think. But I feel like I'm not gonna, I don't want to like dive too much into this because it takes a whole lot of time and we can kind of pick our own way. So I think I might give you book homework tonight. I gotta look at it during the break. So you might not even have WebAssign, but yeah, for me, definitely choose whatever way you want. I'll look at WebAssign. I'm not sure. I think of the homework, I'm just going to give you some problems from the book, and you can do it however you want. Okay. So definitely not this way, right? Because this, the other way with right endpoints, that was just I squared as opposed to I squared minus 2i plus 1. So I think, yeah, we're gonna have a lot of terms. That's just a mess. That guy's a mess. I mean, you can do it. I mean, that's just a lot of algebra there. Okay. So here's my advice. If I ever start you at 0, do right endpoints. All right, they're all going to work like this one for the most part. If you think about it, if I start at 0 and do right endpoints, then you're going to have an expression like that. Whatever the width, if it goes from 0 to 5, then it's just 5 over n, right? And then this expression becomes pretty easy too. That would just be 5 over n times I. Okay, so it's a lot easier this way. The only thing we have to consider now is what if I don't start at 0? Then we're gonna have to think about those, because when I is 1, like let's say I go from, we'll do this after the break. Let's say my interval is 1 to 4. So that means when I equals 1, you have to be either at 1 or, which would be the left endpoint, or you would have to be at x equals 1 and 2 over n, if that makes sense, right? That's the right endpoint. It's you start at 1 and then you move to the next guy, right? And if it's, oh wait, 3 over n, sorry. This width is 3. So it would be that. Do you want to deal with that if you want to go to the right endpoints? All right, so that's the only thing we got to talk about and figure that out. Not easy, not easy. Go ahead, Lindy.
What does I like represent?
So you can think of I as like your variable. It's called the index of summation, right? So when I say I goes from 1 to n, I think of it as like a variable like x. But for a continuous function, x can take on, if you can hear me, I'll be right back. Okay, okay. Can you hear me? Give me a thumbs up if you can hear me. Yes. Okay. Good. Yeah. So the question is, what's I represent? So then you can think of I as like your variable, right? For a continuous function f, x is your variable, and x can take on any value. You can think of I as your variable, but instead of I taking on any value, it only takes on integers up to n, and then there's a built-in sum, right, from the problem. So I is always start here, go here, and then start counting. So it's really your natural numbers up until you get to this part. So it's really the only thing that's varying. It's your variable if you want for these kind of problems. Does that make sense? 1, then 2, then 3, then 4, then 5, all the way till you get to n. All right, good. We need a break. It's 4:32 already. Yeah, let's go to 4:40. 8 minutes. 4:40, we'll start again. All right, guys. Let's take a look at something a little bit more complicated. I think that was too easy. All right, too easy. Let's take a look at something that's a little more challenging. Nah, let's do an easy one, then a hard one. Do an easy one first. We'll see if you can figure out the easy one. Okay, first a couple things to get to from your textbook. This is your notation that I'm using for the most part. This one they're going to use M and big M because here's what they're saying: the limit, if you do the lower sum, is equal to the limit as if you were to do the upper sum, which is just equal to the limit. Okay, so that
I don't think you're sharing your screen.
Thank you. This is one of your slides. It says formally that the lower sum, so they'll use this little m sub I for your x's, meaning whatever. It doesn't necessarily mean right or left. It depends on if the function's increasing or decreasing, right? So if it's an upper or lower, it doesn't matter because this says right here that they're the same. Okay, it's just equal to the limit. So you can do the upper lower part doesn't matter. The right endpoint, left endpoint does matter. Well, I should take that back. That also doesn't matter. They're still equivalent in that you're going to get the same sum. You want to pick whatever is going to be easier for you. So try this. Find that area for me. See what you get. The exact area from 0 to 1 under the curve f of x equals x cubed. See if you can follow that same process. F of, right, you want to do your width. 1 minus 0 over n. And then if you start at 0 and do right endpoints, your representation of x sub I should just be 1 over n times I. And then you'll have to look up your formula for x cubed, for I cubed rather, I cubed. Here, let me put, and if you didn't write those down, let me put that up here for you. By the way, you should have a decent guess at this guy, right? If you just draw a box, the area is 1, right? And that looks like it's definitely less than a half, right? So I would say somewhere between 0 and a half. See what you get. Okay, how we doing this one? Megan, can you give me the next step here? What do you do next after what I have on the screen?
Can you hear me? Am I okay?
How about that? What's that equal to?
F of I over N.
Mhm.
Is that just 1?
Yeah, here's my function.
X.
So you gotta plug this thing in, right?
I'm
So-
not sure.
So f of I over n means you plug it into your cube function. Does that make sense? What happened to Kevin? Kevin disappeared. Ella, what's f of I over n?
Would it be 1 over n to the third times n squared times n plus 1 squared over 4? I guess you could combine that, but
Well, at first you just get I cubed over n cubed, right? Does that make sense? You might be going
Right.
ahead a little bit. But if
I
you
just broke it up into 1 over n and then I instead of
Oh,
putting them
okay.
together.
Yeah. No, that's good. And then you have a times a 1 over n. And in this case, there's no pluses or minuses, so I can factor out the n. So I should be looking at 1 over n to the 4th. Oh, I forgot my sum. Limit as n goes to infinity, as I goes from 1 to n, of I cubed. What do you think? And now we can use our formula. We again, the goal for a lot of these, well, really the goal for all of them is to find this guy. So once I find that guy, I can replace it with what it's equal to. So I got to rewrite everything else. 1 over n to the 4th, limit n goes to infinity. Sum's gone, sigma's gone, right? Because it's equal to this thing. It's equal to n squared times n plus 1 quantity squared divided by 4. Okay, who's got questions? Oh, I got a mistake. I got a little carried away with my factoring out. I can factor the n out of the limit, or I'm sorry, I can factor the n out of the sum because the index is I, so I'm allowed to factor n's out, but I can't factor the n out of the limit because I'm taking the limit as n goes to infinity. So this guy got moved out too far. Sorry about that. He should still be in the limit out of the sum. All right, I can't factor an n out of a limit if I'm taking the limit as n goes somewhere. So he should remain there, and he should be squeezed in here. Okay, and now I'm hoping, well, what's the limit? Anybody get it? What do you get after that part? Can you see it now? What's the answer? Is it 1/4? You see the 1/4? The numerator is a 4th degree polynomial. The leading coefficient should be 1, right? If you square that out, n squared plus 2n plus 1 times n squared, n to the 4th plus whatever, doesn't matter, right? Because on the bottom, I got a 4th degree polynomial. So, I mean, if you want to, let me do it because it won't take that long. But you don't have to do this. In the numerator, I got n squared times n squared plus 2n plus 1. And on the bottom, I got 4n to the 4th. And then I run, this is what I've been skipping. I just want to show you why I'm skipping it. N to the 4th plus 2n cubed plus n squared over 4n to the 4th, the limit as n goes to infinity. right? What I'm saying is I can see that my coefficient in the numerator is 1. The coefficient in the denominator, the leading coefficient is 1. The leading coefficient in the denominator is 4. And then it's a 4th degree in the top and the bottom. So my limit's just going to be the ratio of the leading coefficient. So I'm pretty happy I can go from here to my final answer. Or if you want to be sure, find those coefficients, in fact, multiply them out. Okay, so if we start at 0 and we go to whatever, then you're going to get this pretty often. Something looks like that, like I over n or 2i over n or 3i over n. And you're going to get this pretty often, f of this term. Okay, that's if you start at 0 and you do right endpoints. If I start at 0 and do left endpoints, I just want to avoid that because I got to do the I minus 1 thing, right? Which just makes way more algebra. And there's no need, right? There's no need to do it that way because I should get the same result. So I guess my last thing I got to talk about is what happens if I start at 1 or 4 or 5. Okay, so let's do one of those. I want to do, let's do 25 minus x squared from 1 to 4. 25 minus x squared from 1 to 4. Okay. The widths are easy. Widths are easy. Adrian, what do you think? What is the width of each of our rectangle going to be? It should involve an n.
Would it be change of x equals 4 minus 1 over n?
Correct. Very good. Right. Change in x equals 4 minus 1 over n, or 3 over n. Okay, so the 3 is the width of the interval, broken up into n intervals. Okay, now here's the hard part. If this were 0 to 4, the heights of all my rectangles would be f of 3 over n times I. However, we got to get to 1 first, right? We got to get to 1 and then do that index thing. Okay, so does it make sense? I got to move one spot to the right. So does it make sense that it would be, well, let's just try this. Let's just see if it works. I still want to do right endpoints. I still like the right endpoints thing. I think it's going to work out for us in the end, no matter what. So can I get to the first right endpoint by first going to 1? So I start at 1, and then add to that my right endpoint, right? Which would be the plus this expression, which that expression, if I start at 0, I just use that expression. But this will give me a way to get to anywhere, right? Doing the right endpoint thing, just adding that number to it, right? And does that work? Well, when I is 1, then if I do this picture, right? So the 1 moves me automatically to here, and then this thing just moves me through the interval at 3 over n widths. We could try to do the left endpoint thing, but I think it's easiest just to stick with right endpoints. And by the way, this makes the problem significantly more difficult because we have to square this thing, which is a binomial term, as opposed to just squaring 3 over n times I. So if I have to start at a non-zero number, it makes the problem significantly more difficult. But the good news is most of the time we can get to those endpoints by using this concept. Just add the first number to it if we were to start at 0. right? And then the rest of the work is the same. It works the same. However, it's going to be more work. It works the same. It's just more work, right? So let's see. Astrid, can you set up my representation of the area? Area equals what?
The area equals the limit as n approaches infinity times the sum I equals 1 n of f of 1 plus 3i over n
Very good. Times.
3 over n.
Very good. Excellent. Everybody follow that? That's how it works. Those are the widths, those are the heights. Okay. Now for the messy part. F of 1 plus 3 over n. Maybe I'll come over here and work that out, and then I'll replace it. F of 1 plus 3i over n, or 3 over n times I, same thing, is 25 minus x squared, but x is this thing, 1 plus 3i over n. Okay, and that's why if you don't start at 0, you just got to deal with it. It's going to be more work, right? Because we have to do that shift. When we do the shift, I got to FOIL out the 1 plus 3 over n times I. It's going to give me 3 terms, right? It should give me an I term, a constant term, and an I squared term. And then we can deal with the ends later. So let's take a look. Just be careful when you FOIL if you want. Set yourself up. 1 plus 3i over n, right? That's what 1 plus 3i over n squared means. And that's going to be, you're subtracting that. So again, be careful. 1, that's the F in FOIL. The I would be a 3i over n. And let me write them out because we got to, right? That's O in FOIL, I in FOIL. And then we square the last term, 9i squared over n squared. Okay. Let's go ahead and add these together. That should be 6i over n, right? It's common denominator. And then I run the negative through. So I got minus 1, minus 6i over n, minus 9i squared over n squared. And then ultimately, I have the following expression for my area, where my function is 24 minus 6i over n minus 9 over n squared times I squared. All of that, right, because that's the height of each rectangle, all of that times the width of each, which is 3 over n, which we could have factored that out right away. We should probably get in the habit of doing that. That's coming out, right? We can always factor out our n terms. We're trying to isolate those I terms, isolate those constant terms. Any questions on that? Does that make sense what I did so far? It's not easy. Right? And you know what you want. I want to sum with the 24 by itself. I want to sum with I by itself, and I want to sum with I squared by itself. Right? That's the goal. So my 3 over n's coming out of side of sigma. Oh. Long problems. Okay, so be careful. Be organized. The limit as n goes to infinity. 3 over n. Sum I equals 1 to n. All right, tell me if you like this. I'm going to try and break them up now. 24. I need a sum that has an I. I need a sum that has an I squared. Factor out. Remember that 9 over n squared is just times the I squared, so I can't pull it out of the whole thing. The 6 over n is just times the I, so I can't pull that out. Okay, who's got questions? Now we can get rid of our sigmas. All right, we got a formula for each of those. You see if you remember your formulas yet. The limit as n goes to infinity of 3 over n. That's just 24n. Remember I. Go ahead, Lindy.
Why did it change from plus to minus or minus to plus?
Good question. It shouldn't have. You got it. Those are negatives. Minus and minus. Good. The sum of I, right, was n. That was the Gauss problem. N times n plus 1 over 2. And then I squared, do you remember this one? N times n plus 1 times 2n plus 1 over 6. I'm going to have to check my memory of that one. I think that's right. N plus 1, 2n plus 1 over 6 for I squared. Okay, good. Let's see, what am I missing here? 3 over n times that one times that one times that one. I guess I'm missing that parenthesis. Deep breath. Now, fine. Well, almost calculus. Almost calculus. I think I'm going to at least run that 3 over n through before I take the limit. And that's why I want you guys to keep writing limit, right? If you don't rewrite the limit, then that tells me that you already took it, right? So make sure you rewrite that. That should just be 72, I think.
And shouldn't it still be minus?
Thank you. I don't know why I keep doing that. Too much sums in my head. Differences. Okay, sorry, I am back. 6 n times 1, I guess times the 3 would give me 18. 18 n plus 1 on the bottom. 2 times n is 2n squared. And we could have simplified, I think, ahead of time, but that's okay. 3 times 9 is 27. And on the bottom, I got a 6n squared times an n when I'm running this guy through, right? And simplifying 9, 3 times 9, 27, n plus 1, 2n plus 1. I think that's right. N times n squared, n cubed, 6n cubed. What do you think? Now, I probably want to simplify. You take the limit now and then simplify. I'm going to try and simplify. That goes away. That becomes a squared. I'm going to take 3 into both of these. That's going to be a 2. That's going to be a 9. That goes away. That's into the first. That's a 1, and that's a 9. Okay. Let me know if you see something you don't like. 72 minus 9 over n. n plus 1, that should be an easy one if that's right, minus 9 over 2n squared, and then a n plus 1 times a 2n plus 1.
I got a question.
Yeah, go ahead.
Should the where you have 9 times n plus 1 over n, should that just be 9 times n plus 1?
Right here?
Yeah, like the bottom one. Because you had it as 2n squared, but shouldn't that just be 2n? Oh, never mind. I think I see what you did.
Yeah, so
Yeah, I
so
think
I
you're
had an 18, and then I had a 2, and I reduced that to 9 over 1. I had an n over n squared. I reduced that to 1 over n. Does that make sense? I think that's right. And now to take the limit. Now to take the limit. Let's see. We could write 3 limit terms. We're just going to take the limit of each. So I got 72 minus 9, right? The limit of this, because power is the same. And then this one would be what? What do you think? Minus what? Careful, it's not 9 halves. What do you think, Joni? You got an answer for this guy? What's the limit as n goes to infinity of this thing?
I don't have an answer, sorry.
It's okay. It's a tough one. You got the leading coefficients. You got n squared over an n squared. So can you see without fooling them out that you get an 18?
Yeah, so 18, so it would be 9 again, right?
Very good. Very good. I always like these ones. Weird area, and you end up with an exact integer value for the area. I'd always think that's pretty cool. If you looked at this area, here's a picture of it. That guy. 54 square units. That's 25 minus x squared. Okay, we are just about out of time. I'm not gonna do WebAssign homework. I'm just gonna give you a ungraded book homework, and I got a sheet of paper too. I think the book's actually pretty good. Here's your homework. Since these take forever, and I'll post this in an announcement right now. Hopefully you guys, can you get the page numbers in your book? Actually, I don't know if you can. Your book's weird online. I don't know if you can do, I think you can, but I'll just take a screenshot of these and put them in an announcement. Okay. It's page 268, 47 through 56. I'll just give you one hint. Look for symmetry. It could save you some trouble, right? That is, if I gave you, for example, for that one, 25 minus x squared. If I say there's a couple of these in there, what's the best way to approach it? We haven't even talked about going back to negatives yet, but would it make sense that the area here would just be 2 times the limit? Well, how about without writing all that out, 2 times the area from 0 to 2. That makes sense? If you can see it's symmetric around y, then if I can reduce the work, I always want to start at 0 if I can. If I go from 0 to 2, then I can just double it, right? Because it's symmetric. Oh, that's right. You do have a hard copy. It's symmetric. So just find this area, and then this area is the same. Okay. So here's your homework. That's not a whole lot of problems, but they take a while. Okay. And this will be, I'll put you in groups and make you do this on the quiz on Thursday. Okay. So 268, 47 to 56 all. All right. See how it goes. Have a good couple of days. I'll see you on Thursday.
Bye. Thank you.
See you guys.
Thank you.
Thank you.
Bye.
Thank you.
Mister.
Hey, Gabby. You got a question? Oh, you're leaving.